All right.
Hello, everyone. Today we have Florian Riedel, who is going to talk about deformation theory of infinity coalgebras and Mandell's theorem. Thank you.
All right. Yeah, thank you so much for having me here today. Um, as already announced, I'm going to talk about coalgebras, and if there's time, I'm also going to talk about the theorem of Mandell and like possible current ongoing work on expanding it, so to speak. But to just sort of like set the scene, I want to tell you about like what is the basic kind of question we're answering in this work. And for that, so let's say let X be a space or anima or whatever the current hot terminology is. And fundamentally, what we want to do is compare two invariants of that space. So you want to compare two invariants. One of them is the p-complete suspension spectrum of your space, which I'm going to denote as sphere adjoint X, p-complete. And we want to compare this with the chains on that space, the FP value chains, which to keep consistent notation, I'm going to note as FP adjoint X. And P throughout this is a prime, as you can imagine. So I want to compare these two invariants, and it's clear that you can get one from the other, namely you can go from the suspension spectrum to the chains by tensoring with FP. Um, and I want to ask basically, is there a way to go back? So I want to ask, so the question is, can we recover the spherical chains, spherical homology from the FP homology? Yeah, and I'm gonna say chains and homology and like all of these, I'm just using interchangeably to denote like the spectrum, basically. So there's no pi star statement anywhere. If I say homology, I just mean the spectrum. Can we recover this? And ideally, I would like to recover this in a functorial way. And well, the answer is kind of initially, so like the sort of preliminary answer sort of preliminary is no. Not as modules. Right? If you only consider them as spectra, as like an FP module or a module of a p-complete sphere, then there's just like this process of tensoring to FP just strictly loses information. And the reason is quite simple. Basically, since any FP module splits as a direct sum of shifts of FP. But this is not true over the p-complete sphere. Yeah, I mean, you see this over ZP, is that like it's just not every ZP module is free, but over FP this is just true. And I think like a minimal counterexample, right? The point is just that spaces have like K invariants, they are glued together in non-trivial ways, and you don't see this over FP. And I think the minimal counterexample, so to speak, should be like you take the spherical cochains of RP2 to complete it. This just doesn't split as the two completed sphere like this, like as modules, this is not the same, but of course, the F2 homology of RP2 does. Shift here. Yeah, i.e. there are several lifts. Uh, there exist several lifts of F2, the F2 chains. Oh, sorry, there's an unnecessary two completion here. Of the chains, the F2 chains on RP2 to be complete, the two completed sphere. Yeah. So as modules, there's just no chance this loses information, but it's not hopeless. Otherwise, this would be a very short talk. We have an additional structure of homology. Have additional structure. Namely, on this level of spaces, we have the diagonal map. The diagonal map on any space. This induces by Ironberg-Silver. This induces a map. Let me write this maybe as just sphere adjoint X to sphere adjoint X tensor X. Yeah, this is the statement that the chains of a product of spaces are the tensor product of the chains, and this is just true over any base and any generality. If you don't take homotopy groups, this is just true. And so we have like a co-multiplication on the homology, and even more. So the homology of X has a natural E-infinity coalgebra structure. Basically deduced from this diagonal map and the map to the point. And also when I say coalgebra, algebra here, I always mean E-infinity, everything as derived as possible. And also everything is commutative. Right, so recall what is a coalgebra. It's maybe not so commonly encountered as a notion. So if C is some symmetric monoidal infinity category, the category of coalgebras, denote this as CC-alg C. There's just kind of no good notation for it. You just have an extra C. Is defined as what? You take commutative algebra objects in C op, and then you op again. So this is the double op is just so it's like maps are still like covariant with underlying maps. Yeah, and what this is like, what is this data? How you're supposed to think about this? So you have a coalgebra A in particular. This comes equipped co-unit map from A to the unit of C, co-unit, and co-multiplication going from A to A tensor A. And because it's infinity, it also provides you with factorizations like this. And now you have to take homotopy fixed points of C2. Yeah, factorization like this. And of course, it goes on for like higher arity operations. That's how you're supposed to think about it. And so the basic idea is that, like I said, there's an additional structure, namely the coalgebra structure on homology. And this like moduli problem, right? You can ask how many things live over the sphere that lift the homology becomes much more rigid if you consider it as like, if you ask how many coalgebras exist that lift the homology. And so it becomes in fact so rigid, it becomes unique. And this is like the main result of my paper on this. It's called like theorem by me. Is so for all spaces X, the coalgebra take a p-complete suspension spectrum of X. This is a coalgebra in spectra p-complete in connective p-complete spectra. Uh, this is up to contractible choice. The unique coalgebra with an equivalence. That before equivalence, when you tensor with FP, it becomes equivalent to the FP homology of your space. It's now a coalgebra in connective FP modules. So that's quite good. It's in some sense kind of surprising that it rigidifies it so much. But you could even say more, and this is the functoriality aspect I was describing. Moreover, um, for any A in a coalgebra in P-complete connective spectra, it's just a business where the notation is horrible. Always carry around too many adjectives, but so it goes. You have a natural map. Um, if you look at coalgebra maps of A into P-complete suspension spectrum, you have a natural map down to maps of FP coalgebras. We base change A and then put the base change here. This map, like the natural map, is an equivalence. And this is kind of the functoriality aspect, as I said. It describes it as a kind of right adjoint, which we can make even more precise. Yeah, this really tells you that there's really no information lost when going from when tensoring with FP in this sense. And just as a remark, to like say to which degree this was unknown, for algebras and cohomology, this is known already in some sense. Oops. This is known up to the sort of caveat that, of course, cohomology does not base change correctly, right? Like up to the fact, like the dual, like which I mean by this is known is that like the sort of dual statement of this is known up to the fact that, of course, the cohomology, which I noticed the power in general doesn't base change correctly. Um,
So
so in
there is a
general,
question in the chat. So is
yes.
the left-hand side map in C-alg and the right-hand side in FP coalgebras?
Yes. Yes, exactly. Um, yeah, I will some like it gets even uglier if you always carry this notation around, so I might suppress it in points. But one thing to notice that for coalgebra, there's no like restriction of scalars because that's only lax monoidal. So in some sense, there's almost no ambiguity in which to interpret, like which category a certain coalgebra is in. Um, so yeah, but that, of course, I'm just being lazy, so maybe I can write here P complete and here FP, but it's all in coalgebras. Coalgebras. Right. So this is new in terms of it's like sort of the pre-dual story of what we already know for cohomology in some sense, but not all coalgebras are not the dual of algebras, so this is in some sense genuinely a different situation. Okay, so let's sort of package this statement in a little more systematic way. Um, this is kind of the crucial, like one of the insights here is that uh, so we have an adjunction from coalgebras in P-complete connective spectra, coalgebras in connective FP modules, where the left adjoint is space change and the right adjoint I will denote W. Uh, it's an ugly W. And so I call it W uh, for two reasons. Namely, it kind of behaves like Witt vectors, but also it kind of behaves like Weil-restriction. Crucially, this is not induced from restriction of scalars. Yeah, this adjoint is kind of conjured up by the adjoint functor theorem, and it doesn't exist on the module level, and it does something weird. But since it does something weird, it also does something interesting. And in this case, it wants to produce unique lifts for you, which is why it's the Witt vectors. But if you think about how the duality works out, upon dualizing, it should be a left adjoint to base change on algebras. So it's kind of like a Weil-restriction type thing. Called W. And so what is the like more systematic approach to the first thing I wrote? Let me rephrase it like this. So it's another theorem. So the basic strategy is you show that there's a like a good subcategory downstairs on which W actually produces lifts, and then you show that homology lies in there. So there exists a full subcategory which I call formally etale coalgebras. Formally etale lying in all connective coalgebras. Um, such that W, like this right adjoint I described, from this category to coalgebras and P-complete spectra is fully faithful. And for all x, any space x, the homology of x is contained, lies in the subcategory. So that's like the more, I mean, of course there exists such a subcategory. This is maybe a bit poorly phrased, but like we have a condition for something to be formally etale, and the homology of a space satisfies this condition. It's not just the empty subcategory, which was probably be a legal choice. Okay, so this is like the more systematic way to phrase it. And so yes, yeah, and this is like something about the theory that makes it a little nicer than in the algebra situation, because in the algebra, like you can interpret the like Witt vectors or spherical Witt vectors as a kind of left adjoint in some sense, but it doesn't exist in this full generality. And here you really just have a right adjoint, just always. You don't really know what it does, but you know that on the things you're interested in, it actually produces like unique lifts against the base change thing. That's how you should think about it. Okay, so
I
that's a
have
nice
a
theory. Yeah.
quick question. I should still not think about this as induced from restriction, right? This is still
Yes.
not okay.
Yes, extremely not, right? Because then it
Okay,
would be the identity and underlying. One thing you can kind of immediately convince yourself
right.
of, right? So you just like the fact that it can't be restriction, right? So the FP is the terminal coalgebra over FP, and the same for the P-complete sphere. So you can see immediately that like W of FP, just because it's a right adjoint, will be the P-complete sphere. So
Right.
it has to do something strange, basically.
Yeah. Okay, cool. Thanks.
Right. Okay, so it's a cool theorem, but how do we approach it? So the approach to showing this goes as follows. So you can write the P-complete sphere as a limit over its Postnikov tower, all the way down to the zero truncation of the P-complete sphere, which is just ZP. Oh, oops, no, go away. which is just ZP. And then you're at ZP, and of course everyone knows that the limits that ZP can be written as the limit of its like p-completion tower. ZP, which is just FP, of course. And so each map in this limit tower is a square zero extension. And this means we can use deformation theory. So deformation theory, in some sense, is just a theory of how to lift stuff against square zero extensions. And what stuff here is going to be is, well, either the coalgebra itself or maps of coalgebras. We'll investigate how to lift them. Do you mean to write truncations? Oh, yes, I did mean to write truncations. Thank you. I always get confused, right? So it's less or equal 1. Yeah. Yes, sorry. I mean the one where you cut off about above a certain thing. Okay, so the basic strategy is you define formula etale coalgebras, figure out what the hell that should mean. Second is show that formula etale coalgebras lift uniquely and functorially against square zero extensions, which I will abbreviate terribly like this, against square zero extensions. And then the last step is, of course, showing that the homology of a space is formula etale. Right. That's the general approach. And so a lot of this like higher deformation theory stuff is kind of buried in DAG 13 and DAG 8. No, not DAG 8. DAG 9. It's buried in the DAGs. Safe to say. So I will give a little interlude on this. That just does not say interlude at all. It still doesn't, but a little interlude on deformation theory. So of course, classically, right, a map of like ordinary discrete rings is called a square zero extension if the kernel I satisfies I squared is 0. This is probably most everyone's familiar with. But this is certainly not coherent enough to cover this this Pasnikov tower, right? This is like the crucial insight is that the Pasnikov tower is actually composed of square zero extensions in like higher algebra land, but in you know cowardly old algebra, this is all you need to say. And the classic examples, of course, include like the split square zero extension, the split zero extension where you just take the direct sum and you write down the formula for multiplying that makes it square zero. It's quite easy to do, and the thing that we already had above is the mod p map from z mod p to the n to z mod p to the m minus 1, and this has kernel I is z mod p. And in fact, this construction induces a functor. This induces a functor from, and to be consistent, I will write mod heart for like discrete modules over a discrete ring to commutative algebras augmented over R. And let me write heart to say, indicate that everything's discrete. taking I to the split square zero extension R plus I. And in fact, it has an inverse, which just takes an augmented algebra like this to the kernel. Yeah, this is an equivalence. It's like a classical result. You can prove yourself. It's a fun exercise. And now to like get this thing sort of deformation theory in E infinity land, there's a, or like to make sense of a square zero extension in E infinity land, we can kind of cheat. Or like, I mean, that this way we don't really know how to write this down in terms of equations. This is hard. But we can just like promote this observation to a definition. And there's a theorem by Lurie, which says that if R is an E infinity ring, we also have an equivalence. I can just remove the hearts in this above thing between R modules and oh sorry, I'm being this is not an equivalence up here. Sorry. This is I messed up. So this is a construction, this is a functor, and there's a functor in the other direction. Um so sorry. And the point is you can check that. Oh, yeah, this is an important point. Of course, the right hand is not a module category. You can check that the split square zero extension defines an abelian group object in augmented algebras. This is the crucial point. It defines an abelian group object, and once you put abelian group objects, then it becomes an equivalence. Yeah, this is crucial. Yeah. Okay. This observation, which again you can prove yourself, it's a fun exercise. You could promote this to a definition almost in the sense that R modules are equivalent to the stabilization of commutative algebras, like augmented algebras over R, such that if you take like the underlying infinite loop object of a module Rm, I mean just write it like this. This is the same like as a like just on spectrum level, this is a direct sum like this. Right, so you can just define, in some sense, once you have this theorem, it's like a little bit cheating, but to have this theorem, you can just define the split square zero extension as take the underlying loop object of a module in this sense. It's a bit abstract, but you can do it. And what does this like stabilization condition tell us? Or like the fact that it's the stabilization of augmented algebras, what does this tell us? It tells us that we have pullbacks in ooh, boop, 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 in commutative rings that look like this. Yeah, so you can like if you take these pullback diagrams, it just shifts the module around basically. And then you can use this to define a general like sort of twisted square, like a general square zero extension as a twisted split square zero extension. So this to another definition, and this is also due to Lurie, which is a map pi of R eta to R of E infinity rings is a square zero extension with fiber I if it sits in a pullback diagram. Like so, over here you put pi and pi, R and R. And here you put the split square zero extension, but shifted one up. And the maps are once the identity, like the zero section, so to speak, And here is some section called eta that may or may not be non-trivial. Oh, yeah, m is equal to I. Yes. I decided to change my notation from the thing that I've written before. Big mistake. Yes, exactly. If it sits in a pullback diagram like this. So you can imagine like the split square zero extensions kind of as E-infinity group objects in augmented algebras. So like in some sense, yeah, it's like a group object, and the split square zero extension is like a torsor under that thing that's being classified by this map right here. Yes. This is how you make sense of square zero extensions as generality. And the point is that like the reason I'm telling you is that examples are of this are ordinary square zero extension. And more crucially, this now allows to take us to the Pasenkopf truncation of a ring. Like so, and this will have fiber pi n of r sitting in degree n. So any connective infinity ring you can think of as being built up iteratively by like attaching the homotopy groups in a square zero way. And this is one of the reasons that like higher algebra of connective things is in some sense much easier than non-connective things, because you can always just start with pi naught and go up, so to speak, using some sort of deformation theory argument. Okay. All right, what do I want to say now? Okay, so this is all fine as well. I've defined this for you, but the point is that so this perspective on square zero extensions is quite abstract, and it's like if I give you a map of rings, you may have a hard time telling me whether it is a square zero extension or not. But luckily, there's like more condition, like there's more explicit conditions for checking it and so on, which I won't go into detail here because we don't need it. But the point is that from a theoretical point of view, it's very helpful. Think about this, and especially for coalgebras, like sorry, for things that are sort of built out of modules using like a limit-friendly way, you get like direct access basically to their deformation theory from this definition. So again, we want to fundamentally use the following fundamental theorem, which is again still due to Lurie. Yeah, so there's the functor from the connective algebras to let's say cut infinity, which takes a connective ring to the category of connective R modules. This is, by the way, the reason I have to say connective all the time in this deformation theory story. It's wrong if you don't say connective. This functor commutes with these pullbacks. The pullbacks that I drew above, they're called small pullbacks, doesn't matter. And this kind of formally just immediately implies that this is also true for the functor coalgebras in connective modules. So we can reduce, this lets us reduce question like let's say lifting along arbitrary square zero extensions to split ones. And in particular, yeah, I don't want to say this. Let me see so I didn't get messed up. So let me write out just, okay, this is gonna look terrible. Let me write out what this means. Yeah, this means for such a coalgebra, sorry, for such a square zero extension, I get a big pullback diagram. Or either here and commutative algebras, sorry, coalgebras in our modules here and the same here. And here. Now here goes R plus a shift of I. You have like this, and the maps, the functoriality is all base change. It's all base change of coalgebras. And so what are we really trying to do here? We're trying to lift along square zero extensions. So we take a point A living inside here, and what we're trying to compute is the fiber up here. Yeah? We're trying to compute the space of lifts of R living down here to a coalgebra up here. And by lift, I mean if you base change it back down, you have an equivalence. And so this lets us compute um, if I so like let's denote so A in here. Oh, that's not what I wanted. There you go. If A in here goes to, let's call this A eta, and A in here goes to like let's say A0. Remember these two maps into the target were potentially different. Um, this computes the fiber as the space of maps uh, A eta to A0 lying over the identity from A to A. Yeah, and this is now suddenly something reasonably explicit, right? You had like this fiber category, but now you've reduced the problem to um, computing a certain mapping space, which Marian ranks easier. And this also tells you that in some sense, lifting objects is really equivalent to lifting maps up to a shift. This the shift you're really seeing in this like shifted I by one. And this is why like if you ever look into classical deformation theory things, there will always be like, you know, like lifting maps of things will be classified in some sense by homology groups, and then lifting objects will be classified by also by cohomology groups, but there's a shift appearing, and this is essentially due to this observation. Okay, I'm running a bit low of time, so let me get back to coalgebras, but this is like sometimes you can deduce, like if you can play with this sort of pullback a little bit and think about more deeply, um, you can deduce a lot of like classical deformation statements by thinking about this. It's very, very useful. Um, and if you do this, you might come to the following conclusion that this is again back to coalgebras. Coalgebras. This is a definition, also due to me, which is so for a connective so R connective E infinity ring. Yeah, I promised a definition of formally etale coalgebras, and I'm going to give it to you. So A and A is a coalgebra and connective R modules. Yeah, for some M connective R module 2. So write E for the zero section. Yeah, we can take the zero section from R into the split square zero extension by R. Or zero section, what I previously denoted by I it comma 0. Then just like before, we have an exjunction. Yeah, from coalgebras connective R modules. And so we can base change up to coalgebras over the split square zero extension. We can base shape out, and in some sense, this is like the trivial lift. of R to a coalgebra over the square zero extension. And we have a junction back down, which is this mysterious right adjoint, which we can sort of should be thought of as Weil-restriction. We have this junction, and we set and this is like very suggestive notation, which I can justify further. Loops infinity A of M. This doesn't mean anything. It's just a notation. Define this as you take A and you base change it up, and then you right adjoint it back down. And you can sort of check formally that sort of if you have a map, if you have a map phi from some other coalgebra to A, you can look at the space of lifts, so the space of deformations of phi from like to some square zero extension. Yeah, let's just say to the split square zero extension. Then you can compute this as the space of lifts in the diagram. Uh, ah, in a diagram like this. This is like the kind of if you play around with adjoints for a while, you can see that you can just like yeah, that's just what this sort of weird adjunction playing around does for you. It produces the takes like this lifting a map across like different categories and makes it just into lifts in a commutative diagram in one category. But you have to go through this coalgebra right adjoint. There's just no other option. Okay, this is a lot of stuff. So now the point is we call a formally etale if loops infinity A of M is just A for Rm, any connective R module. And then somehow by this thing here, this will sort of tell you that you can uniquely lift maps into A against any square zero extension. Yeah, just because it's equivalent to this lifting property in the category of coalgebras, but then like this map, if it's just an equivalence, of course, lifts are unique. Yeah, there's nothing you can do. Okay, and this seems kind of stupid as a definition. Like it's like well, it seems a little strange, and it is strange. So let me remark the following. Um, remark for an R algebra, S, yeah, in the algebra land, because restriction of scalars is Lax-monoidal, it is just like it's just induced. The right adjoint there is just induced from that. Um, the right adjoint is just induced, so the analogous like criterion would be that the map like that S is equivalent to what? To S, and then you tensor it up and you just forget back down, but this looks like this. Would be this condition. And this is obviously nonsense. This just straight up implies that S is zero. Yeah, so like this might make you a little nervous that this is like a nonsense condition which is never satisfied, but it's really the strangeness of the right adjoint that makes it work. So to like appease you a little bit, let me tell you that this is not an empty or boring condition. So so recall that so for there exists in this algebra situation there exists a module called like a S module called the relative cotangent complex. Also of S relative R, and this is the thing which controls the formations of S. Yeah, and then maybe in algebra land, S would be called formally etale if this thing vanishes. Now, this is the classical algebra thing, and there there's many good, like, this is certainly, like, in particular, like in etale extensions of like discrete rings will have this property, or like, yeah, this is like a very reasonable condition. And then basically what you can show to tell you that the definition I gave above is kind of at least inherently something reasonable that you can ask, namely if A coalgebra over R is dualizable. Yeah, namely the underlying module is a dualizable module, which is the same as a compact module, or if you want to think about chain complexes, this is the same as like um, what is it, like finite projective in every degree or something. There's a chain condition where I mess it up. Yeah, if this is dualizable, so you're basically in a land where algebras and coalgebras are really dual to each other in the sense that the R-linear dual, take like the R-linear mapping spectrum from A into R. This will then be an commutative algebra in R modules. Um, if dualizable and dualizable, and we have that for a dual, the relative cotangent complex vanishes. Um, then A itself, the coalgebra, is formally etale in the sense of definition above. Yeah, so this is something that's like this is the easiest sort of example you will get of a formally etale coalgebra. But there's certainly a lot of these. So it's like it's not a vacuous condition. And then the next thing you show is that like I said, which I hinted to earlier, um, yeah, it is that formally etale coalgebras admit unique and functorial lifts against square zero extensions, and sort of the lifts are sort of exhibited by Weil-restriction, aka by these weird rider joints. They are the ones doing the lifting, so to speak. Yeah, and this is just in some sense it's a formality. Like from the lifting statement, you show they lift uniquely, and then you have the statement on mapping spaces, and then it just kind of tells you that it has to be a rider joint which is doing this. And by the way, a similar statement is true for like ordinary Witt vectors. If you think of them as like Witt vectors from FP to ZP, if you think of them as like derived Weil restriction, then then yeah, it's the same kind of formality that, well, it has to be a left adjoint in that case. Okay. Yeah, so for those who are paying attention, like this upper proposition, so let's call this position star. So it's just known that for all x, like the relative cotangent complex over FP vanishes. So proposition star implies that for all compact spaces, the FP homology is formally etale. And that's very nice, but certainly like it should have nothing to do with, I mean, so the reason I say compact is, right, of course, once you go to homology, you become dualizable. But of course, this should have nothing to do with compactness, and indeed, it doesn't. And this is like the insight. So to get all spaces, you need to take care of Einberg-MacLane spaces, basically. Yeah, so KVN for V is some FP vector space. And the way you do this is so there's a recent okay, so it's like if you think about if you know how this is proved, this result that the cohomology is formally etale, basically you see that there's a Frobenius map on cohomology as a power operation P0, and it's an isomorphism on cohomology of a space. But it's also zero on the cotangent complex. So the cotangent complex is a functor. So if it's zero and an isomorphism, the cotangent complex has to vanish. And this is kind of using this computation like this. This is like if you want to credit it, it's Mandell Lurie in some sense. Yeah, Mandell doing the first bit with the power operation and Lurie kind of putting it together. Um, and so some of the analogous statement for coalgebras was recently proved by Tom Bachmann and Robert Birkeland. So theorem by Bachmann and Birkeland, which says that the homology of such a KVN essentially sits in a pullback diagram, where on the right you take the co-free coalgebra, yeah, the right adjoint to the underlying, taking the underlying FP module, and it sits in a pullback diagram like this, where F is some sort of Frobenius map. So this whole thing is called the Artin-Schreier map. And the point is this whole formally etale condition plays much better with limits than with co-limits. Yeah, if you knew it played well with co-limits, then you would be done after finite spaces in some sense, because every space is a filtered co-limit of finite spaces or compact spaces. But it's more better behaved with limits. And the idea is basically you can understand, like you have to deal with the right adjoint, and basically you just know what the right adjoint does to this side of the diagram. You can just work it out. Like it preserves core-free coalgebras and it interacts with the Frobenius in a way you can get control over. And this basically lets you prove it for all Einberg-MacLane spaces, and then you kind of go from there to all spaces, which is very similar to how the dual proof in algebras works. Basically, once you have Einberg-MacLane spaces, you kind of win. Yes, right. So like this side plays well with Weil-restriction, aka the right joints. Okay, so I think I have like 4 more minutes, if I'm not mistaken. Um, so let me say a couple of words. This extends to, so there's a question whether this extends the result to all spaces or just nilpotent spaces. And this, you can extend it to all spaces. Basically, the point is you can write a space as a, like, can take its pro-nilpotent completion. And this will, in some sense, induce a isomorphism on pro-homology coalgebras, and then you materialize, and you just you can write any space as a limit of like the homology of any space is a limit of nilpotent spaces, and you just win. Once you get Einberg-MacLane spaces, it's so over. They can't stop you anymore. Well, pro objects are still stopping me a little bit, but it's like almost done. Um, yeah, so let me just say like a couple of words about Mandell's theorem. So an Abel statement in the let me say it in the recent version, which is again due to Bachmann-Birkeland, which is that you have a fully faithful functor. Yeah, you can take p-complete nilpotent spaces. That's why the nilpotence is coming up to coalgebras in modules over FP bar. The functor is just takes x to the FP bar homology. And this is fully faithful. And we can also characterize its image. This is like the coalgebraic version of Mandell's theorem. And now you can kind of descend the statement. So you can descend this down to FP, a version of the statement. It will not be fully faithful over FP. And then you can lift it to the P-complete sphere to like coalgebras in P-complete spectra using the technology I explained today. And this all goes towards this is current work in progress with me and Thomas Nikolaus, which would realize an idea of Thomas, which is so this all goes towards realize the slogan, basically a space is a coalgebra in spectra with trivialization of the Tate-Fabini. Now this is like just a slogan at this point, but there is like a coalgebra Frobenius, which is better behaved over the sphere. And so you can descend your state like this embedding up here, you can descend it to FP, and then you use this like Weil-restriction spherical width vectors thing or whatever to lift it to the sphere. And you kind of identify the descent data you had to input with this Frobenius. And then you undo the descent data and you get like a description of the category of what that point P-complete spaces, but then you can you do the usual factor square thing. Well, this is sort of in progress. It's no longer, why is my pen no longer writing? It's telling me I should stop. I just unscrewed it. How did I do that? That's crazy. Okay, my pen is no longer writing, but I'm basically done anyway. Yeah, thank you. Should be now.
Thank you very much.